Now we've learned about what it takes to generate the angles associated with a sine wave. So let's look at generating sine waves themselves. The sine wave itself is really just an unwrapping of the circle that we have to the left. So if we take a look at the circle and map it across to the sine wave, you can see that starting at 0 and rotating counterclockwise direction, we can draw a complete circle. This rotation then represents one complete cycle of generating a sine wave of voltage or current. And you'll notice here that the length of the vector or the phasor on the circle out to the circumference exactly relates to the points on the sine wave as they're being plotted with time. So the radius of the circle could equal the maximum or peak value of the sine wave. The other thing you'll see here is that the angles that are represented on the circle as the phasor traverses around the perimeter of the circle or the circumference, if we stopped it at each point, 0 to 0, 90 to 90, if we stopped it at 45 and come across, 45 would be right there. 180, we're back to 0. 270, we're back at negative on the sine wave, and then back to 0 over here. So we've got a one-to-one correspondence between the angles and the circumference on the circle that we have with the sine wave. And the thing to keep in mind is that the height of the sine wave here, the amplitude, matches the projection of the height on the circle. And what I mean by the projection is this, where we have E, is actually a projection from the y-axis. So how would we determine what the instantaneous voltage would be, the little e? What would it be on the sine wave as it relates to the circle? Well, we can write the expression that the radius is equal to the peak value. Well, so the peak value is the length of this phasor or vector, and it would match up exactly here on the sine wave. So to determine that projection, it becomes the instantaneous value, or little e, which is a sine relationship. So we're back to that sine function. So if I take the peak value, multiply it times the sine of the actual length of the vector, I will get the instantaneous value. So E, in this case, is equal to 100 volts times the sine of the angle that we happen to be making at that point. So as we rotate our phasor from 0, the radius of the peak voltage then becomes the hypotenuse of the right triangle. So we have the hypotenuse, which is the fixed value or the fixed length of that radius, and then we have two components. The x-axis actually is the cosine component, or that projection, and the e value is our sine value. The vertical component e then is the height if the sine wave of the sine wave, it should be of the sine wave, at any instant of time, and is called the instantaneous value of the voltage. And so it will change with time. You'll notice here that the instantaneous voltage is increasing from 0 to its maximum value, or 100 volts, at 90, and then it starts to decrease again. Then it goes negative. So notice that the voltage E peak is equal to E, the instantaneous value, at 90, and the negative value is negative E at minus 90. So it becomes a projection of, in this case, just the y-axis that becomes the instantaneous value. So time and frequency become very important components for the sine wave. The axis here, the x-axis, is typically associated with time. You'll notice on the bottom here we have time 0, time 1, time 2, time 3, times 4, and then it would actually repeat itself. So time is the number of, in this case, tick marks along the x-axis. If we look at it from 0 to 4, this would be the time it takes for the sine wave to go through one complete cycle. So frequency and time are an inverse relationship. Frequency is the number of times that a repeated event occurs per unit time. The SI unit for frequency is the hertz, and it actually relates to how many cycles per second, or one repetition per second. For a sine wave, the time it takes to generate one complete sine wave, its cycle, then is called the period. So you can see here that we have frequency is equal to 1 over time, time is equal to 1 over frequency. So as an example, if the frequency of rotation is 250 hertz, 250 cycles per second, what is the period? Well, since we have the frequency given here, let's invert the relationship and solve for time. 1 over frequency, 1 over 250 hertz then is equal to 4 milliseconds. Therefore, if 250 cycles per second occur, the time for one cycle is 1 millisecond. So that's how long it would take for it to go through this one cycle, and then 2 pi again, or 360 degrees later, it does it again, and again, and again, and again, and again, and again, and again, as long as you have power applied. If it takes 100 microseconds to complete one cycle, then what's the frequency? So now we're going to use the opposite expression. Frequency is equal to 1 over time. Frequency then, in this case, 1 over 100 microseconds is 10,000 cycles per second, or 10,000 hertz. So this becomes important most of the time when you're dealing with electronic circuits and you make measurements on something called an oscilloscope. You are going to be measuring in what's called time domain. If you are making measurements on a spectrum analyzer, which measures RF frequency, radio frequency, like from an antenna from a broadcasting station, you will be measuring in the frequency domain. Angular velocity. So we've talked about frequency and time, and we've talked about the number of times that we can end up with one cycle in a given amount of time. Now we're going to talk about the angular velocity, or how quickly it moves through or sweeps through a given set of cycles in a period of time. So when we come back, we'll pick up with angular velocity.